Okay, so now we know how to make polymers, which is through the addition reaction of alkenes. If you haven't watched that video yet, I suggest you go and watch it and make sure that you're comfortable with the idea of choosing a monomer and knowing how we manufacture polymers. But I want to have a look at the types of polymers that we can manufacture and the different properties that we need to know about. So there's really two different types of plastic that we look at, and these plastics are made, of course, by polymers, and these are thermoset versus thermoplastic. One of the easiest ways to think about these is thermoplastic is something that will melt when you heat it, like butter. It will go from being a solid into a liquid. These are the types of plastics that we tend to see, that we've seen great advances in with 3D printing. Okay, so thermomelt plastics are the types of ones that we would see using 3D printing filament, because we can apply heat to them, they become viscous and liquid, which allows us to then push them through a nozzle and use them for 3D printing. Thermoset, however, is something that you see when we heat it, it becomes more rigid and then will eventually decompose. So the analogy that we're using here is like cooking pancakes. You use your thermoplastic butter to melt, to create the surface of which we would then put the pancake butter in, that when we apply heat to, it sets and becomes more rigid. Okay, and what this is a result of is the actual structure of the polymers themselves and the links between the polymer chains. Okay, so thermoplastic is these unlinked chains, sort of like big pieces of spaghetti that are all sort of tied up a little bit, but not necessarily physically connected. In a thermoset plastic, we actually connect the chains with things that we call crosslinks. So let's look at those a little bit more closely. So when we talk about thermoplastics, what's happening is we have all these polymer chains that are there, maybe hundreds or thousands of carbons long, and they're going to be held together by our intermolecular forces. Okay, some of them may be dispersion forces if they're just polymers of ethene. Maybe they'll be dipole-dipole or hydrogen bonding, depending on the groups that are present in our polymer. Okay, but there's just intermolecular forces. There's no covalent bonds. These are just weak intermolecular forces that we know when we apply heat, it increases the kinetic energy, things start to move around, we break those intermolecular forces and we get melting, this phase change. Okay, in the case of thermosetting, these crosslinks are covalent. Okay, these are actual bonds. So in order for the strands to be able to break apart and slide over each other like we see in melting, we would need to actually break these covalent bonds. And what happens is we're actually more likely to, or as likely to, break bonds within the polymer chain as we are between the polymer chain. So we see degradation. Okay, so this is similar to that question we looked at when we talked about the heating of glucose. When we melt glucose, it's the disruption of the intermolecular forces, but when it begins to char and turn black or decompose, then that's because we've hit the heat point where we are starting to break the intramolecular bonds. Okay, so we're breaking the covalent bonds when we start to do that. So if we apply too much heat to a thermoset plastic, it starts to get rigid and then it will start to burn, decompose, because we're breaking the covalent bonds. Whereas heating a thermoplastic, we break the intermolecular forces, it will turn into a liquid. Okay, and then we're able to mold it and extrude it. So that's cross-linking, okay, intermolecular forces or cross-linking. The other thing that can affect our plastic and its properties is the degree of branching. Okay, so this means if I have something like ethene as my monomer, all I'm going to have is hydrogen bonds. I've got no kinks in my chain, no branches hanging off. So what I get is this big long chains of just carbons and hydrogens, with hydrogens sticking off, which don't get in the way very much, so they can stack. Okay, so we get these really nice long chains that can stack closely, so high levels of dispersion forces because they can get close to each other. Okay, and we talked about this with alkanes, that we get high levels of dispersion forces. If we start to stack these together, this means we have high density because we get a high number of things in a small volume. Okay, if we start to add branches onto our monomer, so say we actually have something like this, okay, so what have we got here? We have 1, 2, 3, 4. So 1, 2, 3, 4. This part here, this 2 carbon here on the but-1-ene, will act like a branch. When we form the polymer, it will be sticking up off the chain like these ones here. These branches mean that we can't have as much stacking, okay? So they can't pack together as well. We have weaker dispersion forces because there is less packing, less surface area coming into contact with each other. So these are generally more malleable. We can use them for things like cling films and garbage bags and squeeze bottles. They're going to be softer, a little bit more stretchy. They're not as dense as our HDPE. Okay, so what we tend to find with high density polyethylene, okay, we have high density because they can stack together nice and tightly. With low density polyethylene, it's because we've introduced branching, so now they can't get close to each other. So they have a lower density. There are less polymer chains per volume of polymer. The other thing that we need to talk about is...
Just a sec. Okay, I found this on the web.
Sorry, I activated Siri. Okay, let's look at tacticity. So we've looked at intermolecular forces and intramolecular, talking about crosslinks. We have talked about branching. Okay, so this is how the chains are joined, okay, either by intermolecular forces or covalent bonds. Then density of the polymer chains caused by branching. Okay, the other one that we're going to look at as tacticity, which is the position of groups on the chain. So are they on either side of the chain? Are they all on one side of the chain? Are they randomly across the chain? Okay, so this could be a chloro, this could be a branch, it could be any number of things that we have attached into our polymer to give it particular properties. So the way these side groups in the polymers are arranged has an effect on their properties, okay, particularly if they're polar or something like that. So the terms that we have here are isotactic, okay, iso being isolated, okay, all groups are on the same side of the polymer, so that's this one here. Okay, syndiotactic, okay, syndiotactic, like a syncopated beat, they alternate in a regular pattern. Okay, so this one is syndiotactic. And then the last one we have is atactic. So like asymmetrical, there's no pattern. Okay, these are just random. So atactic is random. Okay, so how these are positioned can change the way that they stack, how closely they get to each other, and how they behave. If we look at an example using benzene as a group that has been added into our polymer, because benzene is very large, we can see the effect that it would have on the polymer structure here. All the benzenes on one side means that we could have something approach easily from this side, whereas if they are scattered across here, we have a lack of approach from both sides. These are large bulky groups that get in the way, so they may change how well things can have dispersion forces, how well things can stack, and therefore how much regularity we would see in the structure. So what we tend to see when we have high amounts of stacking, so the chains being able to form regular patterns and get close to each other, is that we see crystallinity. Okay, so they become clear, we get higher regions of clarity in our polymers, and we can get more rigidity. So when polymer chains align, okay, so they all line up nice and tightly, they become highly stacked regions or crystal regions within the polymer. Okay, so this is going to be a high density again. Okay, so we're going to have greater strength in our polymer, but also greater clarity as well. So no polymer is completely crystalline. There is always regions of turning in the chains and things like that, which we call amorphous. Amorphous being like an amorphous blob, no regular shape. Okay, and we've seen amorphous carbon when we talked about allotropes of carbon. So these less structured regions mean that we don't have that high density areas or rigidity and the clarity. Okay, so if we have crystalline areas, they arise from high regularity in our structure and stacking. So if we look at syndiotactic polyethylene here, because they alternate, we're causing these little cavities where each chain can fit into the next, which gives us a great amount of regularity and structure. So we have a high amount of crystallinity, about 90% with polyethylene, and the crystalline regions are due to this stacking, and we see that for a great level of stacking. So this polyethylene gives us great crystallinity and good structure as a result. Okay, so that's really all we need to know. We need to know that tacticity talks about where the groups are arranged on the polymer. We need to know that crosslinks determine if it is thermoset or thermomelt. I want you to think about, what about polymers that are elastic? Have a think about that, and we'll talk about those in class. And that, so we've got tacticity, crosslinks, and density due to stacking. That these all influence the way we can, due to branching, sorry, that all of these change the way that the polymers can stack and the way that they can move over each other, therefore they alter the properties of the polymer. The more stacking we have, the more crystallinity and more rigidity the polymer will have. The more branching and less stacking that we have, the more amorphous and soft we will tend to find the plastic that results from those polymers will be. And that's really what you need to know. Just taking that a little bit further, okay, just realize that we can react polymers further to put into the polymers different amounts of cross-linking. And this is the kind of thing that we actually see if you have your hair chemically straightened. They are basically they are changing the polymers that make up your hair by changing the crosslinks. If you have it permed, they're doing the same. And also the process that we use to give rubber tires more rigidity and strength when they're heating up on the road due to the friction. Okay, so polymers can react further to create crosslinks between chains. So this is where we react the side groups, okay, further. So we can do chemistry on the side groups if we've added in hydroxyls or chlorines or things like that. Large amounts of cross-linking produce a rigid material, and then the one that we use for doing rubber is called vulcanization, where we cause cross-links to occur between sulfur atoms that are on the side chains of the polymer. You don't need to know this process in detail. It is just an example of further manipulation of polymer properties. So that's it for our polymers. You need to understand how branching affects them, the difference between intermolecular forces and crosslinks, and also the sidedness of our functional groups that are within the polymer. Good luck. You should be able to do Chapter 10 review now.